Hello and welcome to lecture 27 of the course Computational Complexity. So today we are going to start talking about randomized complexity classes, right? So we'll first motivate why it makes sense to have randomized algorithms, and then we will see complexity classes that are derived out of randomized algorithms, and we will see like around 3 or 4 of them uh, in the next couple of lectures, right? So before getting into randomized complexity classes, let us try to see what is the class P, right? A language L is in P, right? A language L is in P if there is a polynomial time decider for that language, meaning whenever X is in the language, the decider accepts. Whenever X is not in the language, the decider rejects X, right? So here in this, I have used the notation A for the decider, and the decider is a deterministic polynomial time decider. What is NP? We had NP is a class of languages that have a non-deterministic polynomial time decider. However, we saw a verifier based characterization, right? What is a verifier based characterization? L is a not NP is a class of languages L which have polynomial time verifiers, meaning whenever X is in the language, there is a certificate string Y which can be used to verify the membership of X, right? So Y, two properties: Y is not too long, Y is length of Y is at most polynomial in the length of X, and two, the running time of the verifier is polynomial in the length of X, right? And also in the length of Y, but then anyway the length of Y is polynomial in the length of X, right? So in this notation here we use V to denote the verifier algorithm. Okay, so we have the two classes P and NP. P has polynomial time deciders, NP has polynomial time verifiers. Okay, now again NP is a class of languages that can be efficiently verified, right? So which means there is a certificate or a proof or a witness, right? These are the three terms that we use to describe the string Y, and once the Y is there, it can be used to verify the membership of X. So for instance, if the problem is testing whether the graph is 3-colorable, the certificate is the actual 3-coloring, or one of the certificates is the actual 3-coloring. So then you can use the 3-coloring to verify that the graph is 3-colorable. If the graph is not 3-colorable, whatever you try, it will not work, right? None of them will be a proper coloring. Anyway, that's a very brief introduction to P and NP. Now let us see what is so NP machines, right? So there are different ways to think of NP machines. So some may say that, so what we said in this lecture is that if there is a correct solution, if there is a correct certificate, somehow the machine magically finds this solution, right? It is that is the power of non-determinism. I have also seen other sources where they say that you can think of it as being able to parallelly test all the strings, all the certificates, right? Or all the computation paths can be parallelly tested. Okay, so these are all different ways to think of non-determinism, right? So I personally do not agree with this parallel notion, because that I think leads to more confusion. I would like to think of it as the machine automatically finds the path using the power of non-determinism, right? So the question is now, what if we do not have non-determinism, right? So it's well established now that non-determinism is some kind of a superpower. What if we do not have non-determinism, right? So one possibility is now, right? So let us motivate randomness, right? So can we not guess the witness string at random? So instead of guessing using non-determinism, what if we use randomness? Can we generate the witness string at random? Then what would happen, right? So what if Y is a like if we know the length of the witness string, or expected length of the witness string, can we not generate such a thing at random using randomness, right? So let us try to see some problem and let's see what happens. So let's see a satisfiability instance. Phi is equal to x1 and x2 and so on till xn, n variables. Is this satisfiable or not, right? Again, this is an easy question in this sense, right? So it's an AND of n variables, obviously it is satisfiable, so it is obviously satisfiable, right? Just set all of the variables to true, right? So the AND is also true. It's an AND function, obviously, right? However, this is something that is easy for us to see when we look at the formula. A computer or a Turing machine doesn't have this kind of a judging capability, right? It just gets something and it has to do a procedure that is generic, right? So it will not be able to look at this and say, yes, this is the AND function, and so it's obviously satisfiable, right? So now what will a computer try to do? Computer, like, if it has to generate the satisfying, so what it may try to do here in this thing, right, in this model about generating the witness or certificates at random, it will try to generate assignments, the true false assignments at random, right? So how many so then what is the probability of it succeeding? So consider an algorithm that generates an assignment at random. Okay, so the algorithm is very simple. It generates an assignment at random, and let's say the assignment is okay, and then if phi evaluates to true, algorithm concludes that phi is in SAT. If phi evaluates to false, algorithm concludes phi is not in SAT. So the algorithm has to decide whether it is satisfiable or not. So it generates a random assignment, it evaluates phi, right? So now let's see what happens in this case. You may be able to guess now what is likely to happen. So the formula is just an AND formula. How many assignments are there? The number of assignments is, there are n variables, 2 power n assignments are possible. How many of them? So phi, as we saw, is obviously satisfiable. How many of these lead to, so we want the algorithm to conclude that phi is satisfiable. How many of the randomly generated assignments lead to the conclusion that phi is in SAT? There is only one assignment, which is setting x1, x2, x3, everything to true. That leads us to concluding that phi is in SAT, right? So there is only 1 out of 2 power n assignments that will lead us to conclude that phi is in SAT. For all the other 2 power n minus 1 assignments, we will conclude that phi is not in SAT. So the probability of success, at least for the above formula, right, for the above phi is equal to 1 by 2 power n, and probability of error, again for the above phi, maybe I'll just write that down, is equal to 2 power n minus 1 divided by 2 power n, or 1 minus 1 by 2 power n. So you see how bad this is, this particular algorithm, right? What we try to do is we have a, so this is it is succeeding, but with a very small probability, right? 1 by 2 power n. So it's 1 by exponential probability, inverse exponential probability, which is very, very small, right? And the rest of the time it is going to the, it is making an error, it is inferring the wrong conclusion, right? So now, so this is the, this is an example of a randomized algorithm. Okay, so now things may seem hopeless, depressing and all that, but actually this is just the starting point and we will see how to improve from here. And believe it or not, randomized algorithms have a, are usually extremely nice to work with. Many times the algorithms are extremely simple to describe, right? So this algorithm, for whatever it's worth, it was, even though the probability of success is not that good, it was very simple, right? You just randomly generate an assignment, you plug it in and see whether it works or not, right? So usually randomized algorithms are extremely simple to describe. You do not need much to, you do not need, it is not so difficult to understand, it's not so difficult to program, right? It's very easy to program, and usually they perform reasonably well. Okay, so again, this is just an exception, but this is just an exception and it's deliberately chosen so that I can see how, I can show you how this can be led to an improvement. Okay, so there is a lot of advantages, there are a lot of advantages to randomized algorithms, and we will see again, this is not a course on algorithms or randomized algorithms, so I will not go into the benefits of that. Rather, we will focus on the complexity classes derived from randomized algorithms. Okay, right. Okay, now let's see what we can do. So obviously this probability of success is poor. So can we improve the probability of success? So one standard trick that is employed in the case of randomized algorithms is to repeat the algorithm many times, and this is also sometimes called, this technique is called boosting. Okay, we repeat the algorithm many times. So let's see what happens. So in this case, what should you do? Like, let's say you repeat it 2 times. Meaning you first randomly generate an assignment and then you again randomly generate an assignment and evaluate phi at both these assignments. So if both of these lead to the conclusion, both of these are phi is evaluated to true, then we say phi is satisfiable. Both of them say evaluate to false, then we say it is not satisfiable. But what if one of them evaluates to true and one of them evaluates to false? Well, even if one of the assignments lead to phi being evaluated to true, that means that's a satisfying assignment, right? So even if one of them is true, then we will declare that phi is satisfiable, right? So just think about this. So even if, so how do we report true or whether the phi is satisfiable or not? We declare, think about why this works. Sorry, we declare phi is in sat if phi evaluates to true in even one of the R trials. So you can think of these as trials, and even if one of these trials lead to phi evaluating to true, then we say phi is satisfiable, right? So when do we say that phi is not satisfiable? If all the R trials lead to phi evaluating to false. Okay, right? So this is the algorithm. Let's try to see what happens. In this case, what happens? Let's say we try this algorithm R times. What is the probability of success? The probability of success, well, it's easier to compute the probability of failure or the probability of error. When does the error happen, right? So notice what is going on here. Whenever we declare that the formula is satisfiable, we will always be, it is always a correct answer, because we never declare a formula is satisfiable unless we have found a satisfying assignment, right? Unless we find the correct assignment, we do not declare that the formula is satisfiable. So whenever we declare it is satisfiable, it is satisfiable. The error happens when, okay, this formula is satisfiable. The error happens when we report the formula to be not satisfiable despite this being satisfiable. So the probability or the problem is when the formula is incorrectly reported as not satisfiable, right? So rather it is a false negative. So right now we are in the middle of the pandemic. The terms false positives and false negatives must be familiar to all. But still, so false negative means that it is incorrectly reported as negative. So it is actually a positive case or satisfiable formula which is reported as non-satisfiable, right? So what is the probability of that? The probability of that is not picking the correct solution in any of the R trials. So it should not pick the correct solution in the first trial, it should not pick in the second trial, and so on. And as we have said, we declare it as not satisfiable only when it evaluates to false in all the R trials. We declare it as satisfiable if it evaluates true in even one of the trials, right? So what is the probability of the false negative? It is evaluating as not satisfiable in all the R trials. So which is, for that to happen in one trial, it is 1 minus 2 power n, 1 minus 1 by 2 power n, as we saw here, right? Sorry, I'll use another color as we saw here. But here we are repeating this R times, and R times all the times the random bits chosen are independent random bits. Okay, so the probability of error is every time it gets multiplied. So there is a R in the exponent here, and you may and this is simplified into e power minus R divided by 2 power n. This is because of this simplification, or this usual simplification that we do. You may have learnt in your 11th or 12th when you learned calculus that 1 minus 1 divided by x whole power x tends to 1 over e when x tends to infinity. So similarly, when n is big and r is big, you can approximate this with e power negative r divided by 2 power n. Okay, this is something we can do. So the probability of error is e power minus r divided by 2 power n. Okay, this is what we achieve by boosting. Now let's see how effectively or how far we have boosted. Right. So what is so let's say, so we want, let's say, very low probability. Let's say for us the probability of error should not be more than, let's say, 0.1, let's say, or 0.2, 0.25, let's say 1/4. This is the ideal probability of error. Okay, say 1/4 is the probability of error. We want to bring down the error probability to 1/4. How? So we need to reduce this quantity e power minus r divided by 2 power n to 1/4, which means we can do some reverse engineering, right? So we can set e power minus r divided by 2 power n should be 1/4, which implies that r divided by 2 power n should be this should be log 4 natural logarithm, which means r should be 2 power n times log 4. Again, it's natural logarithm where the logarithm is taken to the base 2, base e. As I've said before, whenever we use log without qualifying, the base will be 2, but here I am explicitly writing ln and I am explicitly stating that it is a natural logarithm, which means the base is e. In any case, this r, when we want to bring down the error to a constant, happens to be 2 power n times log 4. Okay, so this, what is this number? This is a reasonably huge quantity, right? So when we want to bring down the error to 1/4, we are having to repeat it 2 power n times log 4. But anyway, what we could have done instead is to just try out the 2 power n assignments one by one. That would be just 2 power n times repeating, right? We do not need to do this randomness stuff. So this is not really much of a big deal, right? SAT, we anyway know that, as I described, SAT is in x or x time. X time means it's an exponential time complexity class. So k equal to 1 to infinity d time 2 power n power k. This is x time. But anyway, SAT is in x time, right? So as I described, so what is the benefit of this, right? Again, in this particular problem or in this particular formula, it happened to be the case that searching for a positive or searching for a correct solution was like only 1 into power n. So it was like searching for a needle in a haystack. But there could be other problems, or there could be other instances of satisfiability itself where the probability of success may be much better, right? So this is not a reason to rule out this. This just this happened to be a simple enough example to illustrate. Hence, I took up this. Okay. So what if instead? So here the probability of success in one trial was 1 divided by 2 power n. Right. This was the probability of success. What if the probability, so this is inverse exponential, so 2 power n is an exponential quantity. What if the probability of success was inverse polynomial, let's say 1 by n power k, right? So n is the input length, or here it is the number of variables in the formula. What if it was this, where k is a constant? In this case, we could have repeated polynomial many times, or if the number of repeats was c times n power k using the same limit 1 minus 1 by x, etc., right? We get that the probability of error becomes e power minus constant, right? When the number of repeats is c times n power k, where c is some constant. So if we set c to be, I think log 4, natural log of 4, then we get probability of error is equal to 1/4, which is good, right? So again, in this case, the number of repeats required is constant times n power k, which is polynomial time, right? So again, what was the difference here? We said that the number of repeats becomes polynomial time if the probability of success was inverse polynomial, right? So when does the probability of success become inverse polynomial? In this case, there was only one true assignment amongst many. So if the formula was such that we had many true assignments, right? So it not only should it be satisfiable, it should be satisfiable with many true instances. In such a case, such an algorithm may be helpful. Otherwise, it is not very helpful. But anyway, randomized algorithms, again, as I said again and again, SAT is just a motivating example, and we will use other. It is more widely used for other problems, right? But this I wanted to tell you so that you get some idea of the idea of boosting, and in which cases do the probability of success. In which cases is the probability of success good enough? Right. So now this leads to one complexity class called RP. Okay, RP simply stands for randomized polynomial time. It consists of those languages for which there is a probabilistic Turing machine. Probabilistic Turing machine is it's a Turing machine that can make random choices. That's what probabilistic Turing machine means, which runs in polynomial time. So it must be probabilistic, it runs in polynomial time such that whenever x is in the language, it accepts with a probability of at least half, and whenever x is not in the language, it accepts with a probability 0, which means virtually never accepts. So again, you may see the motivation. We notice that this problem, the problem and the algorithm that we just described, works efficiently when the probability of success was higher, 1 by inverse polynomial and not inverse exponential. So that is why we need, whenever the probability of acceptance, whenever x is in the language, the probability of acceptance should be sufficiently high for the machine. And it's exactly like this, right? Whenever a formula phi is not satisfiable, right? This algorithm will never accept, right? There is no false negative or there is no false positive. We declare that a formula is satisfiable only when you find a satisfying assignment, right? So there will never be a situation where the formula is declared satisfiable while it is actually not. So there is no false positive, it only has false negative. And this definition is also saying the same thing. Whenever x is in the language, it is accepted with a probability of at least half. Whenever x is not in the language, it is never accepted, right? So this is the definition of the complexity class RP, right? So again, we'll see some aspects of this class. The first point is that P is a subset of RP. Anything that has a deterministic polynomial time algorithm is contained in RP. Why? Because you can view the deterministic machine itself as a randomized machine, right? Whenever x is in the language, it always accepts. So the probability of success is actually 1. Whenever x is not in the language, the probability of success is 0. So that is why any deterministic polynomial time decider can be viewed as an RP decider as well. Second, RP is a subclass of NP. Why is this? When is X a subclass of, when is L in the, when is a language L in NP? So whenever a string is in the language, it must have at least one, whenever X is in the language, it must have at least one accepting computation. All of the other things could be reject, but at least one accepting computation should be there. In the case of RP, what we are saying is that whenever X is in the language, around at least half of it should be accepting. The rest we don't care. And whenever it is not in the language, everything should be rejecting, which is the same for RP as well as NP. We want all computation paths to be reject whenever X is not in the language. So when X is not in the language, it is the same, the condition is the same. When X is in the language, RP requires at least half to be accepting paths. NP requires only one accepting computation. So that is okay, which is, this condition is more than met by the RP yes condition. Hence, RP is contained in NP. So this is something that you can think about if it is not clear, and you can ask questions over the forums if this is not clear. So you think about this, please. Second point is that this quantity half here, right, this is really an arbitrary quantity to some extent. We could replace it with 1/10, for instance, any constant, 1/10, let's say 2/3, 1/4, anything, and it will still be fine. We can even replace it with 1 by n power k, inverse polynomial, like we did above over here. Even then it is okay, because the thing is that if we have a machine that accepts with probability 1 over n power k, then you can use boosting to achieve 1 over 10 or 1 over 4, as we just saw. And even the boosted algorithm will use polynomially many trials, so the overall running time is still polynomial. So you can go from inverse polynomial to constant to even something like very close to 1. You can boost up more and more and get very close to 1, like 1 minus epsilon, where epsilon is very, very small, right? Again, so this half is just an arbitrary number, but if you look at textbooks, maybe you may see 1/4 or maybe 2/3 or something for the in the place of half for the definition of RP. Right? So don't be surprised if you see some resource that states a different requirement in this in place of half. It's just because you could move from one to the other just by repeating it some number of times. The boosting I have already mentioned, and it's a one-sided error. So whenever X is in the language, right? Maybe this is best explained by writing a table. So there are two possibilities. X is in the language and X is not in the language. And the algorithm says yes and algorithm says no. So whenever X is in the language, algorithm could say yes, possible. It could say no, right? Because the probability of acceptance is only around half. Whenever X is not in the language, it cannot say yes, it always has to say no. So this is never possible. Okay, so this never happens. Okay, so there is an X and there is another X cross mark that looks like an X, but hope you understand. Right? So this area is never, this outcome is never possible in the case of RP algorithms. So there are two ways to see this one-sided error, right? One is that whenever X is in the language, it could say that it accepts with probability at least half. Whenever X is not in the language, so whenever X is not in the language, it gives the correct answer, right? If X is not, if formula 5 was not satisfiable, it will never say it is satisfiable. So because it's only false negatives. Whenever X is not in the language, it always says the correct answer. Another way to see this is, right, so that is when you look at this grid row wise. Another way to see it is when you look at this grid column wise. Whenever the algorithm says yes, we know for sure that it is a satisfying, the formula is satisfiable. But when the algorithm says no, it could be either case. It could be correctly reporting a no instance, or it could be incorrectly reporting a yes instance. So there are two ways to look at it. One is whenever X is not in the language, it says correctly. And the two is whenever the algorithm reports yes, it is correct. So there are two ways to look at it, and it can be confusing. That's why I repeated 2-3 times already. This particular two different ways of explaining the same thing can be confusing. But then if you think about it a few times, it's not really that hard. This is something to think about. Okay, in the case of RP. And I think I may be going over time, so I'll just conclude this lecture now, and we'll continue in the lecture 28. And I will just very briefly summarize what we did. We motivated the need for randomness as a way to guess the solutions that are magically guessed by the NP machines. And then we saw that it is better if there is some guarantee, it will perform better when there is some guarantee of success, right? So when there is a formula that has only one satisfying assignment, it was not performing that well. But when the formula had sufficiently many satisfying assignments, we saw why it performs well, right? So accordingly, we define RP to the class of languages that for which we have randomized machines which run in polynomial time and which have a reasonable measure of success. So where we allow false negatives but do not allow false positives. So it's a one-sided error. And we also described the boosting that can be used to increase the or reduce the probability of error or increase the probability of success, and this can be done to some extent based on the resources that we have. And yeah, that was the summary of lecture 27, and I'll continue in lecture 28.